Okay, another dynamic programming problem. We have two strings A and B. And we want to find the smallest sum of removed letters to make them equal. So to remove, we have to compare and do this optimally to find the minimum remove sum. So let's look at the problem. How can we compare the strings? Intuitively, you look at this, and with your naked eyes, you can try to compare them, and you see that there are some equal letters and some different. However, this problem can't be done in just one single pass because it's a dynamic programming problem, and given the two strings, to compare them we have to define some indices, and for the suffix of each we know that the solution is stable and can be memorized. So this is the entire problem, and it's pretty much mechanical works to write this code in a depth first search by IJ, and now you compare the letters. If A equal B, then you just skip, and if A not equal B, you have to choose which one you take and which one you remove. So if you remove, you making it like this, plus DFS next, or this is minimum, B and J plus DFS next. And for the next, you increasing the J or I. And this is entire solution. Now let's look at my code. And this is how it looks like. I just defined this DP array, DP hash map, and this is a K. We only have 1000 items. Then you have to especially carefully be with these corner cases where one of the strings is ended and you have another string still going on. You just take this code to remove it, and if they equal, it is optimal to just skip them. However, you also can put this into this minimum just to like if they equal, we can set 0 plus DFS. Otherwise we can't do this. So this is entire solution. It's kind of accepted in the, it's not very performant because it is a hash map, it's slow, and DFS recursion also has some performance hits. Now let's look at optimal solution. It is bottom up DP. Let's look at my Kotlin solution. So it is the same, but it is optimized. Now let me show how I did this optimization step by step. So initially I just rewrote it into bottom up DB, and for the corner cases we have to do this pre-filling, filling up the first row and first column, and we go not from the end, because the bottom up goes from the end to the first element, and bottom up solution goes from the first element until the end, and the end is the result. I also use this forward writing to just simplify how the code looks like. And this is a table of DP, and it has this +1 because we're doing forward writing. And then we can put this for loop inside, or rather this loop inside this if condition. This is how it looks like. I have to give up the forward writing for this because it is a special case for the first column. And then we can space optimize it. As you can see, I already applied this %2 trick to just, it was the indexes, then I just wrote this modulo division and it's already accepted, so I can use just a single array, or rather 2 of them. Now we also can a little bit reverse the problem. And if we find which parts to remove, instead can find which parts to take or keep. And what's interesting is that the part we are keeping are equal. So kept A is kept and kept B are equal. And this is a known problem, lowest common substring or lowest common subsequence, and it has a pretty much known solution with the same dp a, I, and j of n squared, and the solution looks a little bit shorter because we don't have to prefill the first row and column. Let me find it. Here it is, and it's only 4 lines of like 4 wide lines of code, and the final step, this is a common subsequence length, and for the common subsequence we have to multiply by 2 because we have 2 of them, like 1 and 2. So we have to multiply by 2. And then we have to also find this sum A and sum B. And the result is sum A plus sum B minus 2 LTS. So this is kind of brain teaser solution, but it is shorter because the LCS is simpler to write. We just have to compare if the letters are the same, we take them, and if not, we skip either one or the second, the first or the second. So that's it for today.